Okay, in this video I'm going to talk about the Desargues theorem. So basically we have two triangles, triangle like this and a triangle like this. And so we consider the lines connecting the corresponding vertices of the triangles and the intersection points of the corresponding sides. So basically we have, so let's denote it A, BC, A prime, B prime, C prime. So we connect the corresponding vertices. So A with A prime, so like this, B with B prime, and C with C prime. And we take the intersection points of the corresponding sides. So this point, so this is the intersection of AC and A prime C prime, then the intersection point of AB and A prime B prime, this would be this point, and the intersection point of BC and B prime C prime, so this point. So let's denote these points by so let's denote this T, this point T, this point R, and this point S, and this point. So this is kind of a single point. So we don't yet know that it is a single point, but in case that when these three lines intersect in a single point, when A prime, B prime, and C prime, when they intersect in a single point, we will denote this point by P. And so the theorem basically states that theorem states that the lines A prime, B prime, C prime intersect at a single point if and only if, so in both directions, the statement, like we have two converse statements, if and only if the points T, R, S are collinear. So lie on a single line. So there is this line. So if if A prime, B prime, C prime intersect at a single point that I denoted by P, then TR and S lie on a single line, and conversely, if TR and S lie at a single line, then the lines A prime, B prime, and C prime intersect at a single point. So, okay. So let's prove this, and the proof will use the Menelaus theorem that I proved in one of the previous videos. So I will remind the Menelaus theorem. So the Menelaus theorem says that if we have a triangle and we have 3 points on the sides of the triangles or their extensions, then this point lie on a single line if and only if so we have let's say T, E, F, and we have so this is the Menelaus theorem that we are going to use. So T, E, F are collinear if and only if the ratios of BD over DC, the ratios of the vectors CE over EA, AF over FB is equal to -1. -1. So the vectors, so basically we go like clockwise from starting from point B and go around the sides of the triangle. So BD over DC, CE over EA, AF over FB, and the vectors, the ratio of the vectors differs from the ratio of the length by a sign. So if the vectors, so let's say if BD, so for this ratio, if the vector BD and DC point in the same direction, BD and DC, so in this case they are in the same direction, then this ratio is positive, and if they are in the opposite direction, as in the case for this ratio, CE is point here and EA point here, so they are the point in the opposite direction, so this ratio is negative. So okay, so this was a reminder. So now I'm going to remove this. So we start the proof like in one direction. So we assume that, so let's we assume that these lines AA prime and AA prime A prime, B, B prime, and C, C prime intersect at a single point. This intersect at a single point, and denote this point by this point by P, like on the picture. So now we need to prove that the points T, R, and S lie on a single line. They're collinear. So I will remove this line so we don't yet know that they lie on a single line. Okay. So now we write the Menelaus theorem to three triangles. So we apply the Menelaus theorem for three triangles. So for triangle PAC and line A prime C prime, for triangle I will leave a space. So for triangle PAB, well, let's start with PAB. So PAB and A prime B prime, PBC and the line B prime C prime, and the triangle P let's write it as PCA, and the line C prime A prime. So for this we have, so let's look at the picture. So we have the triangle PAB, so this triangle, and the line A prime B prime, so this line. Right, so it intersects the sides, or the extensions, in this case the extensions of the sides of this triangle in this point A prime, T, and B prime. So the Menelaus theorem would be, so let's start with A and we go clockwise from A. So A prime, so A prime, and vector over A prime B, multiplied by B prime over B prime P, multiplied by PA prime over A prime A is equal to -1. So this is the Menelau's theorem. So now so the second triangle would be PVC, so this triangle, and the line B prime C prime. So again, this line intersects the extensions of the sides and the points B prime, R, and C prime. So the Menelau's theorem would be so let's start from the point B and go clockwise. So B, so PR over RC multiplied by C prime over C prime P, and B prime over B prime B. Is equal to -1, and the third triangle is PCA, so this triangle, and the line A prime C prime, or C prime A prime. That I selected yellow, highlighted yellow on the picture. So now we have so we start from A and go clockwise. So A prime over A prime P multiplied by PC prime over C prime C multiplied by CS over SA is equal to -1. So that is the Menelau's theorem for these three triangles and three lines. So now we need basically to extract from these three equalities okay, I made an error in the first Menelau's theorem. So here we have, so the intersection of A, like, because T and A prime are kind of close to each other, so I mixed T and A prime, I mixed these 2 points. So AB intersect the blue line at T, not at A prime. So AB, so the first equality should be like A, not A prime, but AT over TB. Yeah. Okay, so now from these three equalities we extract the ratios that involve the 3 points that we need, so T, R, and S. So in the first equality this is this ratio, in the second equality this is this ratio, and in the third equality this is this ratio. So basically what we need is we want to apply the Menelaus theorem now to these 3 points and the triangle ABC. So the triangle, so now we like the converse statement of the Menelaus theorem. So basically now we apply, well, the Menelaus theorem there, it's kind of in both sides, so both the direct statement and the converse statement, they're both called the Menelaus theorem, but we need the converse as opposed to what we already used for. So we used the direct statement 3 times for the Menelaus theorem for these 3 triangles. Now we're going to use the converse statement for another triangle. So apply the Menelaus theorem for the triangle ABC and the points T, R, and S, right? So these points lie on a single line, they are collinear if and only if, or we need only if. So again the triangle ABC and T, R, and S. So we start from A and go clockwise. So AT over TB. So let's write this. I guess we'll make a separate picture. So we have the triangle ABC and the points somewhere here T, somewhere here S, and somewhere here R. So that is the picture. So, and the Menelaus theorem says that they lie on a single line if AT over TB multiplied by BR over RC multiplied by CS over SA. So we need to prove that this is equal to -1. So if we prove that this is equal to -1, then the points T, R, and S would lie on a single line by the Menelaus theorem. So we don't yet know that this is equal to -1, but we need to prove this. Okay, so let's calculate this product of the ratios. So now we extract the ratios, these three ratios from the three equalities that we wrote, the Menelau's theorem that we wrote for these three triangles above. So the first one, we notice that AT over TB, this is exactly this first ratio, AT over TB. So this can be replaced, so we rewrite this by so we write -1, or I guess minus, and then we write the basically the inverted two other ratios. So B prime P over B prime multiplied by A prime A over PA prime. So this I rewrote the first ratio using this equality, right? So now the second, similarly the second ratio, BR over RC, this is exactly what we have in the second equality. So this can be expressed as minus C prime P over C prime multiplied by B prime, no, not B prime, but B prime B prime B over PB prime. And the third equality, the third ratio, so this one, CS over SA, this is exactly what we have here, and so this would be equal to minus A prime P over A prime multiplied by C prime C over P C prime. Okay, so now we look what we have. So we notice that we have almost the same vectors here. So we have A prime A, and here we have A prime. So, but they're opposite to each other, so when we like to cancel, so the ratio of one of them to the other would be -1. So let's write them together. So first three minuses, so three minuses from each of the multipliers, so we get just one minus in front of the whole expression. Then we write this as A prime A over A prime. So we group the vectors differently. Then we have B prime and B prime B. So B prime B over B prime. Then we have C prime and C prime C. So C prime C over C prime. And what remains is so B prime P and PB prime. So B prime P over PB prime. And finally we have PA prime A prime P, so with the vector. So A prime P over PA prime, and finally C prime P, PC prime. So C prime P over PC prime. So now this, let's evaluate this. So minus remains as it is, minus. Now this, now basically each of this ratio is simply minus 1. So this is minus 1, 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 and this is minus 1. And this is because, well, like these are two opposite vectors. So A prime A has the same length as A prime, but it has the opposite direction. So like by definition of the ratio of the vectors, we have minus 1. So basically we have minus 1, minus 1, 3, 4, 5, 6. So 6 minus 1s. Yeah, and this is simply equal to minus 1. So the product of these ratios, we proved that it is equal to minus 1. Therefore, by the Menelaus theorem, the points T, R, and S, points T, R, and S are collinear, and that concludes the proof, like in one direction. So basically, this in this direction. So now the opposite direction is, well, it's kind of similar to what we did in the Menelaus theorem itself and in the Chere's theorem. So we are going to use the direct statement. In the proof of the converse statement, we are going to use the direct statement. And it's not difficult. So again we have these triangles. What was the point there? Okay, T and R. Okay, so this point is T and this point is R. A prime, B prime, C prime, A, B, C. So now we know that these points R, S, and T, they lie on a single line. So we assume that T, R, and S are collinear, and we need to prove that A prime, B prime, and C prime intersect at a single point. So let's say that they are not intersect, they don't intersect at a single point, so like on the picture. So let's say that they do not intersect at a single point. So then what we do is, so we take one of the intersection points, yeah, so let's take this intersection point, let's denote it P. So P is now the intersection point of BB prime and CC prime. We don't know yet if the line AA prime passes through this point. So let's say that it does not pass through this point. So let's assume that suppose that P does not lie on AA prime. So then we draw the line PA. We draw this line PA until the intersection with the line A prime B prime, till this point. No, no. Yeah, until the intersection with A prime C prime. So, and we denote this this point as A2 prime. Yeah. So, and now we considered instead of the triangle, so instead of the triangle A prime, B prime, C prime, we consider the triangle A2 prime, B prime, C prime. So for the, and we apply the, now apply the already proven converse statement of the Desargues theorem, the already proven part of the Desargues theorem. So now we know that for this triangle, so A prime B A2 prime for this triangle A2 prime B prime C prime. So we know that for this triangle, so this, yeah, like it's kind of all points are very close together. It's very difficult to distinguish anything. So T is this point. So for this triangle, instead of A prime B prime C prime, so A2 prime B prime C prime. So we know that, so we see that the lines connecting the corresponding vertices, so A and A2 prime, this line, B and B prime, and C prime, they do intersect at a single point, P. So by construction, they do intersect at a single point. Therefore, the intersection points of the corresponding lines must be collinear by the already proven part of the Desargues theorem, right? So what are these 3 points? So the first, so AB intersect with A2 prime B prime. So we need to extend this point until here. So this point, let's call it T prime. So AB is extended until the intersection with A2 prime and B prime. So T prime, 1 point, and the 2 other points are the same. So now BC intersect with B prime C prime, so this is the point R, and AC intersect with A2 prime C prime, so this is the point S. So from this we conclude that the points T prime R S are collinear. So instead of T we have now T prime. Okay, but by the assumption we have the TR and S are collinear, right? So the line is determined by 2 points only. So in both of these lines we have R and S. So this is the same line. So because basically TR and S are collinear, in other words, we can say that T belongs to the line RS. So like T belongs to the line RS. This is equivalent. And from this we get that T prime belongs to the line RS, right? So therefore all these 4 points lie on a single line. So from this we conclude that T prime, R and S are collinear. All these 4 points are collinear. Okay, but T and T prime are also lie. So T and T prime. So T and T. So from this we get that both T and T prime belong to this line RS. But by construction, T and T prime, what are T and T prime? So T is the intersection point of AB and A prime B prime, and T prime is the intersection point of AB and A2 prime B prime. So, but both of them lie on AB. So both of them lie on AB. So T and T prime lie on AB. Okay, so from this we conclude that this is impossible, because two lines, so RS intersect with AB, we have 2 points, T and T prime. So both of them are the intersection points of the lines RS and AB. Right? So because both of them lie on both RS and AB. So therefore the only possibility is that this is the same point, because two lines can intersect only at a single point. So T is equal to T prime. And T is equal to T prime. This could only happen if A2 prime is equal to A prime, and therefore the whole construction, like originally the line CC prime also passes through the point P, not CC prime, but which is the AA prime passes through P. So from this it follows that A2 prime is the same as A prime, and this implies that the lines AA prime, B prime, and C prime intersect at a single point. Yeah, and this concludes the proof. And so now both directions, both the direct and the converse statement of the Desargues theorem are proven. So that's it for this video.